Okay, so thank you everybody for coming here. We'll talk about network today because it's a topic that's been a bit obsessing for me. And I'll show you like what I've been doing for the past 3-5 years. So I'm Geoffroy. I do cloud stuff. We host your applications at Clever Cloud. And hosting all of that stuff means that I have to mess with protocols and HTTP and proxies and stuff, and I had to get a bit far in Rust networking. So this is a topic that's been very big in the Rust community for the past years. What's async networking? Why do we care? Can't we just think of network in a blocking way? Like I create a connection somewhere or I listen to something and my code is blocking until I get the connection or the data, and it's very easy, very nice to think about. And this is what a lot of platforms want you to do. The thing is, if you do that in Rust, blocking network, it's not good for performance. That's been a problem that's been annoying people for, I don't know when the C10K problem appeared. The idea was like, okay, we have blocking servers everywhere, so we have, for every connection, we need to have a new thread or a new process to handle them, and then the servers got overloaded. And so performance was not great, and someone said, okay, we need a way to accept 10,000 concurrent connections. How do we do that? So we needed another way to think about networking, and the thing is, network is not blocking. That's not how the operating system works. Packets can come here and go there, and all the time, and what your process sees is just a nice view that the operating system is doing to help you do networking, but basically, anything can happen at any time on the network. So, what happens, in fact? You have the OS that receives packets. Like, imagine you want to accept a TCP connection. You have a function to say, I want to accept one. You're not like waiting for a connection there. What happened is like someone did a TCP handshake with your server, and the kernel handled the handshake, and then put the connection in a queue somewhere, and when you do accept, you get something from that queue. So already when you're accepting a connection, a lot of stuff happened before you even took a look at it. And then when you want to read data from the socket, well, you're not waiting for data to happen there. Basically, the operating system received the packet and passed it and put that in a buffer somewhere. And when you do a read on the socket, you get the data from the buffer. So the data was already there for a long time ago. And when you write to the socket, it's not already going to the network. It goes into a buffer. And then the operating system say, okay, I give that to the network at some point, and the packet will go. So whatever you think you do in networking, the operating system is scheduling itself and choosing when it does whatever, and you're not in control of anything. And the nice blocking interface is actually a lie, a very nice lie that we want to believe, but it's a lie, it's not how it works. And when people wanted to get to like the 10,000 concurrent connection problem, they had to remove this abstraction and get a bit lower. So that's where Evented.io came. The idea was that you could register a socket to the operating system and say, okay, I want you to tell me when I can read or write on a socket. And there's a specific error code on socket, like when you want to read data, you can read and read and read and read, and at some point the operating system says would block, which means, okay, I have no more data to give you. You have to wait for the next event when I tell you there's data. And you handle your own scheduling and what you do with the socket yourself. This is what's been done to get like fast web servers. Like this is what you can find in Nginx and in almost any language runtime ever, because it's a bit hard to do, but you get like good performance and you handle like the scheduling yourself. So how we can do? The first method was that to have an asynchronous I/O in your system, like you do the epoch calls. So what I was describing, you wait on events, and then you will read or write to the sockets. This is a bit what I will present, and it's what I've been doing in Rust for some time. Some languages will give you a good, nice interface. So you will recognize this as some Go. And Go has this concept of Go routine, and like it always appears blocking, but you know that it will actually do a lot of stuff under the hood to schedule you and call you back when there's data, call you back when there's a connection. So it makes the code easier to write, but you still profit from the async networking. And what's good in a system like that is that the language runtime gives you a complete abstraction. You do not have to think about what's inside the system, but you get still the benefits of async networking. There's another approach with callbacks. Node.js works a bit the same way as Golang on that, but instead of having blocking code where you call something and then the code will be just stopped, serialized somewhere, and start executing again when there's something, now you receive a callback that you call when you have something to do on this, and you give a function that will be called when there's data, etc. It's at the same time easy to understand and makes the workflow a bit hard to follow. So they went to an async await flavor. Of course, there's the way we do that in Rust with features and combinators. The interesting thing I see with features is that it's not you call the incoming function on listener and then it will wait. No, it calls incoming and then map and then for each, etc., and builds a structure of something that will do some networking at some point. And that structure has a poll method, and we call that poll method, and it will go through all of the steps that were built before. So the server stuff has been built right away, and then we will call the poll method on that. It's a bit annoying to write. You have to move stuff around. You have to actually put stuff into mutexes, which has been annoying to share state. So there's been a lot of work to get to a better syntax by reusing the same features system in an async await syntax. By using the await keyword to do basically what we were doing in Go there. So this will be good. This will be nice to use once they agree on the syntax. There's a lot of problems with features. To be fair, I'm known for having criticized features a lot. I love them, I use them a lot, but I will not shy away from the problems they have and what pisses me off when I'm working with them and what I want to fix. So the first thing is, I told you, when you create the features, it makes a structure that implements poll, but any steps inside your protocol are a structure that implements poll. So when you have a stack trace, you have poll, 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 and poll. Where am I doing what? I don't know. You can try to add functions inside, but basically it's a bit annoying to debug. It's hard to test. This is some code I've been taking from Trust DNS, which is a very great project, by the way, a very great DNS implementation. And they went the way where they create complete mock of a name server to test the client. So you have to have something that implements a server over TCP or UDP for your test. I had to do that for some HTTP stuff, and it makes the test very non-deterministic and very hard to reproduce bugs. So it's annoying. And finally, the typing issues. So, assuming you have, if you know like the import trait feature says, okay, instead of returning the entire type, I will say it's something that implements feature, and I let the compiler like replace import feature by the real type. So if you have two functions that return import future of U42, a number, when you see the code, you say, okay, they return the same type. That's what you will think. But no, they can be completely different type because one of them has a map somewhere and the other does not. So the function that says both, when you want to call one of the functions in one case or the other in another case, it will not compile because both functions have different return types. This is annoying. A worse one is a very simple case I often have to do is, okay, if there's some condition, I return a static value or something I've pre-computed at some point. So result, okay, it implements featured, so it should work. But no, it's not the same type as second. So I have to either box the stuff or do jump through other hoops to fix the typing issues. And this is not hard. It's not just something I have to think about every time I do branching in future. It's annoying. So what happens is like they want you, futures want you to think in terms of blocking I/O. Like you do this and then that and then that, and it's very imperative and it's very nice. But the way they're done match a lot on async networking, and so you have to think about the async networking under that. Like when you debug a feature, you have to think, okay, where did I get the readable event for this socket that triggers this other one to execute that function? And it can be a mess to debug, especially when you're doing low-level development and protocols. I really like features for high-level stuff when I create a HTTP server using a HTTP library, and then I do a call to a database somewhere, that kind of thing, and that can work very nicely. But at a lower level, not so much. So with that, I want to implement network protocols because it's a large part of my work, and I have some criterion. It must be easy to test. Like having to set up server and TCP and DNS and stuff to test anything is a no-go. I want my test to be deterministic. I want my code to be reusable. So features are nice, but you cannot use a features-based protocol outside of Rust. I have protocol implementation I had to use like in other platforms and share between platforms. How can I do that? And how can I make it so that it's not tied to a specific way to do I/O? Because when I started to work in the approach I will present, like it was 2014, like when in 2015, something like that, like the features appeared and said, okay, everybody move to that. And I tried. I say, okay, I want to support that, but I will keep my way there because I want to be flexible on that. So where does it come from? I work on HTTP, which is a nightmare protocol. For reverse proxy at Clever Cloud, it's nice. I encourage you to go look at Sozu. It's an HTTP reverse proxy that can reconfigure itself at runtime, and it's made for load balancing and performance. It's a really nice project, and there's lots of fun stuff to do in that. Lapin, the AMQP library. AMQP is even more of a nightmare to implement. It's one of the worst protocols I've seen. Like everything is in there, everything. And when I started to implement Lapin, it was impossible to do that with features in 2015. Now it might be possible. There are other stuff like the messaging protocol in iOS and Android. I wanted to have the same implementation for both platforms. So I did that in Rust. And so this must be called from C and from GNI, and you have to be flexible on how it works. And of course, there's the sans IO movement that appeared in Python, where they had the same needs, the same approach, because there was all the async await debate in that community too. People had opinions, and some say, okay, we want to do network protocols, but we don't want them to be tied about IO. Because a network protocol is not about input, output, and talking to the network card. It's just a state machine that ingests messages, gives you messages, and updates its state, and you can query that. Like, you can simulate an entire protocol without doing network I/O, and you should. It's not a framework. Often you want to do like the thing you see like in a HTTP framework when you just provide the framework requires that you provide a trait, and the framework will call you and say, okay, this is a request, tell me how you want a response, and I will handle the rest. But like, this is a low-level component. The low-level component should not drive my application. I am in control of my application, and so I will tell the low-level component, okay, now do some work, and tell me where you are, and now I will do something else. And I will make a nice layer about that. But inverting the control like that, it makes everything hard to program. So, no I/O means you can be deterministic. You can make something that's easy to test. You try one input, it should always give you the same output. This is what you want in a unit test, basically. There are still some details about measuring time and random number generation, but these are parts that are easy to mock. So we can make a protocol implementation that's better to debug. And the last thing, they can be represented as code or data. When you see the implementation we had in the different languages, they were just code. So I call something, and then I call something else, and then it's there. In Futures, it generates a state machine, it generates structure that contain each other and call each other's poll method. It's a way to represent state machines. And state machine that can be represented as data can be stored, so you can handle multiple clients at the same point. And you can just create a structure, like create a state, like at whatever state you want, and okay, I want to go from there, I want to send a message and see what happens. Representing a state machine as just data makes it easy to serialize, makes it easy to test. So, to sum up, I want to represent a protocol state machine that just takes message. I want a way to move this message back and forth with the network I/O and with buffers. And I want to separate the I/O layer, because the I/O layer is the responsibility of my application. The protocol should not decide, okay, how many HTTP clients can I handle concurrently? The HTTP implementation that does not decide that, it just handles one client. This is the application over that says, okay, so if I have this many clients, I have to have another thread to handle them. And lastly, how most protocols are specified is with state machines. This is from HTTP2. HTTP2 is a very nicely designed protocol and a complete mess as well, because there's multiplexing. You can have multiple streams in the same connection, and they have flow control, so you can have one stream that's stopped by either the client or the server, while others are running, and you have to handle all the state like that. It's really nice to do. And I have to do one implementation at some point. And you see that it's just, you have states, and you have message, and the state machine specifies, okay, when you're in that state, here are the messages you accept, and where you can go from there if you have one of those messages. So it should be simple to implement. You make an enum with all the states. You have some structure for the messages, and you make an interface where, okay, I give you a message, where are you going from there? So as an example, this is something I have in Sozu. Sozu wants to be very, very smart about performance and how to handle HTTP, so it tries to do stuff with the HTTP connection before having passed the whole connection. Because we receive like some very weird traffic where like one header could be larger than the whole buffer, that kind of thing. So I have a series of states. Like I start my HTTP parsing, I don't have anything. Okay, I try to parse a request line and get into the request line state. Here's a small graph for that. If I pass the request line, I'm passing the headers, and now I'm waiting for header messages. Okay, if I got a host header, I get into the as host state, where I have a request line and the host string. I care mainly about the host and the length information, the content length header. There are a few more steps, but I will not show them then. I will not show them today. And then you can get into 3 different states at the end. So either it was you had no content length and you have just a request without body. You can have a content length with a size, and you have a body of a specific size. or it will just tell you chunked, and then you have to have another state machine to handle the chunks of HTTP. So this should already be simple, but we already have quite some number of states. How do I build something above that? I want to handle a new message and get into a new stage from that. And maybe when I get into a new state, I might have a message to send on over the network. So not really with HTTP there, but like AMQP, when you start connecting to a server, you say, okay, I want to connect. And now there's a set of request replies that start from the server. So the client says hello, and then the server asks a question, the client answers for like 11 steps, I guess, something like that. And so they have to have a way to just send stuff, and it's not only request response. The state machine should also have a way to indicate the IO layer how to behave. Like, okay, maybe I'm receiving a lot of data on this socket, but I don't want to read data from this socket. So I will just tell, okay, now I want to read data. No, I don't. And maybe if the IO layer sees that there's too much IO coming and we don't want to read anything, it will just drop the connection because there's something that's wrong with the protocol. We can do something like that. And we might want to pass messages depending on the state we are in. So the state machine is just something that we query. Do you want to read? Do you want to write something to the network? I have data, how should I pass that? Okay, that gave me a message. What do you want to do with that message? Do you have something to give me to send to the network now? It's just a small thing that you ask and it answers. And from the enum I had there, I can implement a method that will do a lot of pattern matching because we have lots of states and say, okay, I got a request line. If you are in the initial state, you go to the has request line state. Otherwise, if you are in another state, it's an error. You should not try to recover anything because there was an error in the protocol. You stop there. I have the parse method that says, okay, if I am in the initial state, the parser I will try is the request line parser. Otherwise, it will be the header parser, which is over there. So lots of pattern matching. It's a bit annoying to write. I have stuff for that afterwards. I will show you. You can make methods over the state machine to query its state. Like, hey, do you have a host? Like, I want to open a connection to the backend. I have to know which server, which host name you were trying to connect to. So, do you have a host? Okay. So, if you were in as host or as host and length or any of the request types, you can go and say, okay, I have a host. Now I can open a connection to that server. Do you want to read? Well, in most cases, yep. Except I got a full request, or I got a request with a body and there's no more remaining data, or I got a request with chunks and there are no more chunks to read. And this means that after that, I will probably have to read from the backend. So as you can see, it's a bit annoying to write all of those pattern matchings and these enums and stuff and unwrapping stuff from the enum. So I built a small crate that's called machine. Like when I started Rust, I wanted to build this awesome state machine crate that would allow you to write a static state machine that will never get into an error state. And then I left that 4 years rotting somewhere because when you write a protocol, you're not deciding which message will go to your state machine. It's a runtime property. So you can get any crap sent to your state machine at any point. So you have to have something that's a bit dynamic. And so that's why I built a new one that will generate code that matches that kind of programming. So here I specified the same states, what they will contain. So there are a few types overall, like the length info, the length information can be, okay, there's a length, it's a number, or it's chunked. Yeah. This will generate code that looks like that. An enum with some structure. If you want, you can add some derive attributes, and they will appear on the enum and on all the structures. Some helper methods. Or I fixed something yesterday, now it's snake case there. So with this, you can just start in the state you want. So I want to be in a state where I already have a host, so I create one. And then, from there, you already have a lot of things to use, but you want to specify transitions. So I have another procedural macro for that, where I specify the first state, the message, and the outside state. And I can even, for some part, from some transition, I can have multiple outside states, because sometimes there are still conditions inside the message, like if this value is that, I want to be in that state. If this value is that, I want to be in that other one. And it's easier to do in a method that generating like 10 more states for that. And this generates a method that will do all of the pattern matching you want. And now what you only need to do is implement the on request line on the initial state structure. So all of the boilerplate to write state machines is done. And we only had to handle like, okay, I'm in that state, I got this message I'm supposed to get, so what do I do? And this is a very nice way to see, oh, all my states are okay, because I know I can only get to that one if I got that message, and everything else go into an error state that's been added automatically. And to make things nicer, it can generate the graph you saw just earlier. This is very nice to debug because, okay, I write my transition, I want to see where do I go from there, and oh wait, I'm missing a state, why? Or how can I get into the error state at this point? Or am I trying to recover from the error state, should I really do that? You can go a bit far with that. You can also generate some helper methods. So as you can see in the specification, a few of them have a host member, and maybe I want to have an accessor for that. So I will create that, and it will create the host method on the state machine and on each of the required states, and return me known if it's not a state that has that. So with that, it gets a bit easier to write the protocol. It's also very easy to unit test. I can start in the as host state, and I send the length header. Okay, I know I'm in the as host and length state. What happens when I send another host message after that? Well, I get an error. I think there was some case where you could get 2 host headers in HTTP, and some server were accepting that, and this is a bad idea. So you have to go into an error state with that. So we already have like a lot of tooling to build protocols, but it's still very abstract. Like it's only the state machine. How do we talk to the rest of the I/O? Well, first we have to have a way to interact with data. We have to find. I have a buffer. I want to make a structured message from that. I have a message. I want to write that to a buffer. The thing is, we don't know how much data has been sent or not by the network. You could have someone that's very not nice and sends you the HTTP request 1 character by 1 character by 1 character. You could have someone that sends a cookie header that's like 1 megabyte. This happens a lot. So we need some tooling to handle partial data. So a parser that could work with, let's say, okay, this is not invalid because I know there can be more data and I'm waiting for you to read more data. And you need to have the same on the right side that say, okay, I will try to write, and if there was not enough room, I will write the rest later. But you need to handle some state with that. So on the parsing side, hi, I built NOM. This is a nice parser combinator library that's based on macros. And with this, you can build like very fast, very simple parsers. So this is the one to parse the request line. So we try to parse the method, the URI, the version. And if if you only got like the method and the URI and nothing else, it will just say, okay, the result I return is incomplete. I need more data. But if there's even a smallest error, you will say, okay, now you have to stop. This was an invalid message. You have to stop with that. So NOM is able to work in streaming, to work with partial data, and really helps with that type of programming. On the right side, there's the cookie factory crate, which lets you build a state machine. So you see, it's a bit like the futures. I got inspiration from the futures combinator. I built a machine that we try to write. And if you stop like, okay, there was not enough data to write the whole URI, okay, we just have to call that structure later and say, okay, man, now you can write. So this will handle partial data correctly. So from there, how do we interact with the world? We have a very nice protocol that's very nicely stored inside in state machine. So now we have to talk to the rest of the world. So the calling application will just call methods that say, okay, I want you to pass HTTP request. I want you to connect to AMQP server. I want you to create a channel and then send some message on it. So you need to have methods. The method will trigger a state change, will trigger the message sent over the network, or waiting for message from the network. And then you let the I/O implementation run until something happens. This is what happens in any network protocol implementation. Most of the time, we don't see it, because this is the lower level and the annoying part. And this is the part we want to make nice. And once we get into the correct state, we can query that and say, okay, are you in the state I want and do you have the data I want? If not, continue with the event loop, continue doing I/O, and I will call you back later. So the easiest way is you can use those protocols in a synchronous way, in a blocking way. Just have to have a loop that says, okay, read from the socket. Okay, now try to pass that. Send a message to the state. I am in the right state? No. So then I have to read again. It works in synchronous ways. If you're like me and want to have a bit of pain, build your own event loop. So there's this very, very nice library that's called Mayo for Metal I/O. That's at the heart of most async networking implementation in Rust. Like Tokyo and everything is based on Mayo. Mayo is a thin wrapper above EPOL and KQ to handle events. The way you build that is you wait for the OS to tell you, okay, what are the events for each of the sockets I handle? You get an event. Okay, I have this token. This corresponds to this client, this session. I got a readiness. The readiness tells me this socket is readable, this socket is writable, there was an error in that socket and it's been disconnected, etc. You look at, oh, it's a bit larger, but like you look at what you were waiting for, like the interest. So maybe I want a socket that's readable, maybe I have data to write, so I want a socket that's writable. So you match both of them. And you see, okay, so if the socket is readable, I want a socket that's readable, I will read from the network. Okay, that means now I have more messages to send this to the state machine. I have to run my states, my event loop, until there's nothing more to do. And then from there, okay, I run all of the messages. Maybe I have something to write to the network. Can I write to the network? If I can, yes, I will. So this is full of easy mistakes, but it's still a very nice way to program network because you're in control of everything. So I'm writing a lot of boilerplate around that, and we'll probably publish at some point some guidelines on how to write that. But I encourage you to look at how it's done under the hood. That's how people have been building C servers for a while. So there's no reason we can't do that in Rust. There's the callback way. where we get an event loop like that, and we have callbacks that we put on that. Callbacks and closures and stuff are a bit hard to store in Rust, so this might not be the easiest way to write that. But the good news is we can make features around what I just showed. So you can build a feature like the feature trait. It gives you, it requires a poll method. The poll method is just, okay, do you have something to do? Are you in the right state to give me the data I want, etc. And the state machine will say, maybe I have something to give you, or no, I'm not in the right state yet. So you can just wrap a state machine like that and build your own future system. And this is what I did with Lapin, because I made this implementation that's asynchronous, that's very deterministic, and then there's a futures wrapper that's very nice to use because you don't see all of the low-level details. So this is code I got from Lapin that's a bit hard to follow maybe, but the idea is, okay, I want to create a queue, so I will call a state machine and say queue declare. This will create a message that will be put in the output queue, and at some point will be returned by the event loop. And then I poll one function, and every time I say, okay, no, are you in the right state for what I want? Like if you are in the, if you got the queue, if the server answered and told you, okay, the queue exists, now I can return, otherwise, continue. On the parser side, there's a very nice way with Tokyo IO to do that. It's called transport, and you build a structure that has a decoder, and the decoder will get past some data here and there, and you use your non-parser on that data, and it will tell you, okay, I consume this much data, you can remove this much from the buffer, and it gives the messages to your state machine afterwards. So it's a bit of work, but you can make a very nice protocol implementation that's asynchronous, that can be used in C and any other language. That's testable. That can be used with Mio, with features, with everything you want. That's a real pain to write. Honestly, I would like to write high-level code, but for what I want, this is a bit easier. If you have higher level application, write them with async await, with features. If you have low level protocols and stuff, do that. This will be a bit better. And so this was a bit annoying until a few weeks, months ago, but now we have NOM, we have Cookie Factory, and we have the machine crate. So we have the whole set of tools to do that. And if you go look at the Rust Bakery GitHub organization, you will see like I will accumulate a lot of projects around protocols and NOM that will help you write what you want, because there are lots of things you can do with parsers. And I'm all for giving people tools to write what they want safely and fast. All right? So thank you. I will let people... You can clap if you want. Any questions? What about performance with DPDK? DPDK, the IO pass-through for the kernel, was right?
Hello, have you tried DPDK?
Okay, so I have tried DPDK. DPDK is a way to have your packets sent directly from the network card to userland instead of letting the OS parse them. So I did not, but someone has built IP, TCP, and whatever parsers for that. And I know someone is doing like very low-level I/O with NOM, and is not at any liberty to tell which company and which kind of product they are doing. But I know it exists. Yeah. Can I write level 2 protocols? I can write protocol at almost any level. I can handle bit stream parsing. I can add regex in that. I can tokenize a language. It's not the nicest library known for to parse a programming language, but for almost all of the file storage or network formats, it's very good, especially in binary protocols.
I saw there's a Rust implementation of Quick or HTTP3. Is that something that you would want to get done in your state machine?
Okay, so the question, there's an implementation of Quick in Rust. There's actually two. There's Quine and Quish, I guess. Quish. And funny thing is, like the one that from Cloudflare, which is Quish. I don't remember which one. So Cloudflare did one implementation of the Quick protocol, which is a low-level UDP-based encrypted protocol that could be used for the next HTTP, more or less. And they did an implementation like what I presented, because at Cloudflare they want their protocol implementation to be able to be called from C code or Lua or whatever they're doing. So maybe I'll do a quick implementation at some point, not anytime soon. I'm quite busy, but the protocol looks nice. Yeah, it's interesting. Yeah.
Is the machine crate at what level of maturity does it have? How many people are using it?
What's the level of maturity of the machine crate? Not much. I released that last week, and I was still patching it yesterday. But what I've presented, I've been doing the state machine manually for years, so I know it's annoying, it's long, but you can do that and it works. Now that I have the machine crate, I can believe I did that manually, because it's much easier, and I did more and more features. Like, I have methods, I can add a tag to say, okay, implement for all those states, you have to implement the method, and for all those others, here's the default value you can give. There are lots of interesting stuff I want to do that with that. All right, anyone? Okay, thank you.
Super interesting.